Hi guys, today we'll be looking at LIL limits and continuity. And first, let's take a look at the notation of limitation. The notation limit f of x is equal to p says that the limit of f of x as x approaches a is p. We can also say as x approaches a, f of x approaches b. Okay. So when you read these, you don't really need to read limit. You can just say as x approaches a, f of x approaches p. This means that we can make the value of f of x as close as we like to p, provided we choose x values close enough to a. The whole idea of this section is just to prepare for our next section of to check if a function is differentiable at a point or not. Because I'm not sure if you still remember first principle. It states the derivative of a function is defined as as h as x goes to as h goes to 0, f of x plus h minus f of x divided by h. This value will give you the derivative. So by knowing limits provides us with a better understanding of derivative. Okay, example 39, to find limit x approaches to 3x squared. To do that, we just need to substitute 2 inside this expression. 3 times 2 squared is equal to 12, which means as x gets closer and closer to 2, the value of 3x squared gets closer and closer to 12. Example 40, for a function of x, 2x squared minus 5x plus 2 over x minus 2, x not equal to 2. Find f of x as x approaches 2. So this kind, if you just put 2 back to this function, like we did here, put 2 back to this expression 3x squared, if you want to try to put this 2 back to this function, you're going to see it's not going to work, because if you 2 minus 2, look at this denominator, 2 minus 2 gives you 0. And if your denominator is 0, this function is undefined. So to address this issue, we should always, so if ever encounter this case, you should always simplify before you substituting the value. Expand, factorize this expression. We have brackets 2x minus 1 times brackets x minus 2 and over x minus 2. And you're gonna cancel these two. You're gonna cancel the x minus 2 from the top and bottom, which left you with 2x minus 1. Hence, limits as x approaches 2, f of x is equal to 3. Okay, and in the end, you put your 2 back to this expression. To use the graph to describe this function, you're gonna see something like this. And just be noted, the limit exists, but the function is not defined at x is equal to 2. All right. So the limit does exist, but the function is not defined at x is equal to 2. Algebra of limits. In your textbook, you're gonna see something like this, but believe me, you don't have to remember these. It's just too much information. You just need to remember. You can, when you're doing the question, for example, these 3 questions, when you're putting back the value, if it's undefined, you have to simplify. Okay, if it's not, let's just put it in. You get the answer straight away. So like the first one, we put h is equal to 0 back to this expression. 3 times 0 plus 4 will give us, which gives us 4. So there's no problem at all. So let's do this. 3h plus 4. That's just going to be 3 times 0 plus 4, which is equal to 4. Okay, you don't have to remember much things. You don't have to, to do the algebra of limit. Just put it back. Limit x as x approaches 2, for x bracket x plus 2. This is going to be 4 times 2 times 2 times bracket. Here x is equal to 2, 2 plus 2. So you have 4 times 2, 8. 8 times 2 is equal to 16. Okay. Oh no, here. 4 times 2 is 8. 8 times 4. It's not times 2. We're multiplying by 4. So it's equal to 32. The last one, limit x goes to 3. 5x plus 2 over x minus 2. It's just simply 3 times 5 plus 2 over 3 minus 2, 1, which is 17. Okay. And in this example, you're gonna see when you put this number back, especially the first two examples, you put 3 back, your denominator is 0, make this expression undefined. Also b does the same thing. So before putting the value back, we have to simplify. So that's equals to x bracket x minus 3 over x minus 3. So limit x goes to 3, x. So your answer is just equal to 3. Next one, limit x goes to 2, x minus 2 times x plus 1. Let me double check x squared minus 2x plus 1. Yeah, that's right, x minus 2. As simplified, cancel the x minus 2 out. So you have limit x goes to 2, x goes to 2, x plus 1. Okay, so your answer is, put it back, 2 plus 1 is equal to 3 again. Last one, you put it back, there's no, there's no problem. You can't, yeah, you can just simply put it back, okay? 3 squared minus 7 times 3 plus 10 over 3 squared minus 25. So we have 9 minus 21 plus 10 over 9 minus 25. Okay, 9 plus 10, 19, minus 21, minus 2, 9 minus 25, which gives us 16. So your answer is, let me double check. 9 minus 21. Oh, minus 16. No wonder. Yeah, it's one not bad. Okay. And now we're going to introduce a new concept, left and right limits. So when you're taking the limits, actually you can take in the limits from two different directions. One is from left to the point you want. The other one is from the right to the point you want. Okay. So an idea which is useful in the following discussion is the existence of limits from the left and from the right. And they might give you pretty different answers. This is particularly useful when talking about piecewise defined functions. If the value of f of x approaches the number p as x approaches a from the right-hand side, then it is written as limit x goes to a positive, f of x is equal to p. If the value of f of x approaches the number p as x approaches a from the left-hand side, then it is written as limit x goes to a negative, f of x is equal to p. The limit as x approaches a exists only if both the limits from the left and the limit from the right exist are equal. Okay. So this one, limit x goes to a, f of x is equal to p, exists only if your limit x goes to a positive, f of x is equal to limit x goes to a negative f of x. Okay, when you are taking the limits from different direction and they have the same value, and then you can say this x goes to a, as x approaches a, f of x is equal to b exist. So let's have a look at an example. Piecewise defined function. The following is an example of a piecewise defined function where the limit does not exist for a particular value. Okay, it does not exist the limit does not exist for particular value. So we have our function f of x is equal to x cubed, where x is between 0 to 1, and it's equal to 5 if x is equal to 1, and it's equal to 6 if x is between 1 and 2, with 2 inclusive. It is clear from the graph of f that, so this is your graph. So it's very clear from the graph that limit x goes to 1, f of x does not exist, because if you if x is allowed to approach 1 from the left, then f of x approaches 1. On the other hand, so from left to approach this, x is equal to 1, this is going to give you 1. That's, from right to left, so that's x goes to 1 positive. This is x goes to 1 negative. Okay, and this one will give you 6. Also, note that f of 1 is equal to 5. So look at this solid point. So this tells you, remember I said before, this only exists only if, these two are the same. But now they're not the same, so the limit does not exist. So the limit at 1 does not exist. Okay, we're gonna have a look at another topic, continuity and a point. We only require an intuitive understanding of continuity, which means you don't have to get too deep into it, okay? A function with rule f of x is said to be continuous at x is equal to a if the graph of y is equal to f of x can be drawn through the point with coordinates a, comma f of a without a break. Okay, without a break. Otherwise there's to said to be discontinuity at x is equal to a. We can give a more formal definition of continuity using limits. A function f is continuous at a point x is equal to a, provided f of a limits, these two all exist and are equal. Okay. We can state this equivalently as follows. A function f is continuous at a point x is equal to a if the following conditions are met. First, f of x is defined as x is equal to a. And second, limit x goes to a, f of x is equal to f of a. In other words, alternatively, limit x goes to a minus f of x is going to be the same as x goes to a positive f of a. Okay. A. Example: state the values for x for which the functions shown below have a discontinuity. So these ones, they have provided you with graphs, so it's very easy to see. Look at this. Here's the break. So it's discontinuous at x is equal to 1. And here's a break as well. Here's a break as well. So you have two. It's discontinuity. There's discontinuity at x is equal to -1 and 1. And here's a break. So all of these three graphs got discontinuity. All right, let's have a look at the solution. The first one, discontinuity at x is equal to 1 because f of 1 is equal to 3, even though these two are the same, but f of 1 is equal to 3. Yeah, in other words, this f of x is not defined. Yeah, it's not defined at x is equal to 1. Okay. Next one, discontinued at x is equal to -1 because f of -1 is equal to 2. And their limits are not the same when they're approaching from different direction. So from left to right, take the limits from left to 1 and from right to 1. They have different values. And the discontinuity at 1, again, they have this different values when they are approaching from different directions. Okay, so they didn't satisfy the second condition. All right. Okay. At the last one, discontinuity at x is equal to 1 as f of y is equal to 1. And also they have different limits value when they are approaching from different direction. Okay, last example. For each function, state the values of x for which there is a discontinuity and use the definition of continuity in terms of f of a, limits f of x as x approaches a positive, limits x goes to a minus f of x to explain why. Okay. So I've only taken 2 questions. The rest of the question you could explore by yourself. So the first one, f of x is equal to 2x when x is greater than or equal to 0, and f of x is equal to negative 2x plus 1 if x is less than 0. All right. We are making sure, so go back to your continuous, okay? Okay. We gotta have without a break, all right? So we have to have satisfied 2 conditions. One is f of x is defined at x is equal to a. Okay, the other one is limit x goes to a, f of x is not is equal to f of a. All right. Yeah. So to satisfy this one, you have to make these two the same, and also you have to put this value back. So replace x with a. Okay. So, all right. Coordinate, yeah. All right. So now let's have a look at this example. Usually we just take a look at these, terminals. Okay, these terminals. And these two are very similar. To be honest, they're both terminated at zeros. So we first we find f of 0, which is 0 is included in here. So we look at this part of your piecewise defined function. So it's 2 times 0, which is 0. Okay, and then we take the limit. Let's say take the limit from 0 positive. So take a look at the other one. So negative 2x plus 1 gives us 0 plus 1, which is 1. And you're gonna see that your limit is not matching the value of f of 0. Okay, which means if you draw the diagram, when at 0, so it's at 0, but also if you're approaching from right to left, or right to, from the right, okay, you are gonna end up with 1, okay, no matter what this is, something like this maybe. And there's a break, okay, if you draw the diagram, there's a break. So here you can just say, therefore, you can just state this conclusion, therefore there is a discontinuity at x is equal to 0. All right, next one, we're gonna do the same. First, we're gonna find f of 0, which is 0, because we're taking a look at this part. And we'll take a limit, x goes to 0 positive. So again, plus 1. And you're gonna see that's still 1, okay? So this follows exactly the same thing. So therefore, you just write, therefore, write exactly the same thing here. Okay. I think I'm just gonna show another example because they are just too similar. Okay, let's have a look at these this one. Let me take a screenshot. Okay. D. So we've got these two parts. Again, we'll take a look at the f of 0, which is this one. So 0 squared plus 1 gives you 1. And we're going to have a look at your limit. X goes to 0 positive. Negative 2x plus 1 is still 1, right? Because negative 2 times 0 plus 1 is 0 plus 1 is 1. That's really good. We have a good, because it seems like there's no continuity, but we've got to check the other side. X goes to 0 to the 0 minus x squared plus 1. Still 1, okay? So, these two are the same. When you're approaching from different direction, you get the same value. And also at this point, it's equal to 1 as well. So we can say there's no this continuity. All right. Okay, so this part is yeah, let's end up this part. And feel free to ask me any questions. All right. Bye-bye.